In this lecture, we are going to do a small design example of the folded cascode op-amp. So let us take some sample parameters as well as design requirements. So let's first start off with the transistor parameters. Let us say you are given mu and C aux as some 60 microamp per volt squared, mu p C aux is approximately half that, so 30 microamp per volt squared, and let us say the threshold voltages of the NMOS and PMOS are equal and are 0.7 volts each. And let us say that VDD, the supply voltage, is 3 volts, and we also need lambda. So let us say lambda n is 0.1 volt inverse and lambda p is equal to 0.2 volt inverse, and both of these are given for the minimum length of 0.5 microns. So clearly lambda has to be specified for a particular value of length of the transistor. And the requirements, so design conditions. So to make our design look more like a real world design, we are not going to over design, over constrain, because we do not we want to come up with an initial design based on some smaller subset of the real world conditions. So let us say that we need an overall gain of 2000 and the swing limit. So let us say I need an output swing of 1.5 volts peak to peak, and I'm going to give one more condition, which is the power dissipated. The power dissipation in the circuit, let us say, has to be in the core circuit has to be 9 millivolts. Now we want to see how to start off with these and come up with a design example with a particular design. And as you might imagine, as we have done earlier, we are not going to set up some certain set of equations and try to solve for variables, because it's much easier to iterate than to set up the design conditions. So that is kind of the system that we are going to follow. So let us look at the circuit that we have been looking at. We will assume that you are going to use folded cascode op-amp with an NMOS input pair. That will clearly be decided by the input common mode requirements. The NMOS and the PMOS input pairs will have different input common mode levels. Now let us say that we start off by taking the power condition. So the power condition says that this power dissipated is 9 milliwatts and VDD is 3 volts. So both of these together tell us that the total current that can be drawn from the supply is 3 milliamps. And where does this current come from? Clearly this current comes from supply and flows through M9 and M10. So therefore we are going to say I9 is equal to I10 is equal to 1.5 milliamps. So we are going to give 1.5 milliamps to I9 and I10. The total current drawn from supply will then be 3 milliamps. We will be within the power budget. So once we have decided this, we now need to decide how much of this is going to go into the different paths. So let us say that we are going to divide the current equally between the two paths. So let us say this path is going to have 1.5 milliamps of current. In other words, these two I1 and I2 are going to be 0.75 milliamps each. So and I0 is clearly 1.5 milliamps, and of course then I3 to I8 are all going to have 0.75 milliamps each. So now we have set the bias conditions perfectly well. We have decided that M1 to M8, all these transistors are going to have 0.75 milliamps each. M0 is going to have 1.5 milliamps, M9 and M10 are going to have 1.5 milliamps. So we have now decided the bias currents. So the next step, we have used one condition, which is the power dissipation constraint. The next step now is to come up with an optimum with the width and length of the device. We are going to arrive at this from the condition for output swing. So now let us take the output voltage. Now, as you can see, we need to give a certain amount of swing for the upper transistors and the lower transistors. We are going to apply the swing condition to come up with the device size. So the first thing we will note is that I9 and I10 are the largest currents in the circuit. So we are going to say that because we don't want M9 and M10 to become too large, we are going to say that we are going to give them a large VSD SAT, a large overdrive to work with. So to keep the sizes reasonable, right? We are going to say VSD SAT, or I'll just call it V overdrive, which is exactly the same thing. So V overdrive of, we're going to say we'll give it 500 millivolts. And remember that the output common mode is very often under our control. So we're going to say that the output common mode doesn't have to be at VDD by 2. We are now going to say that VOD 9 and VOD 3 and 4 is 400 millivolts. Because these are part of the cascode path, common gate path, we are going to give it slightly higher overdrive. M5 to M8 are purely having a current mirror action, so we are going to give them 300 millivolts each. So we are going to give them 300 millivolts each. So if you actually look at the output levels, the swing, the output is going to swing between two levels. You have VDD minus V overdrive of 9 and 10. So this is VDD, which is 3 volts. And you are giving slightly more than half of that to M9 and M10. So you're going to give them 0.5 volts for M9 and 10. So, and we have now given 0.4 volts for M3 and 4. So that means your maximum voltage at the output can be 2.1 volts. Now what about the bottom side? On the bottom side we have now split the overdrives. So this is ground. We have now said you are going to give 300 millivolts, so 0.3 volts to M5, M6 and M7, M8. Now, therefore, the input common mode is, not the input common mode, the lowest level is at 0.6 volts. Now, that gives us 1.5 volts of allowable swing, which is exactly what we wanted. We have 1.5 volts peak to peak allowable swing. Now, the other thing we can derive from this, now that we have apportioned the overdrive voltages, we can also see that the ideal common mode voltage at the output should be somewhere exactly in between. So, the optimum output common mode voltage should be exactly in between these two, which happens to be at 1.35 volts. So the output should be biased at 1.35 volts. Now to work backwards, we are now going to assume that the op-amp needs to operate at unity gain. So which means the input common mode would be at around 1.35 volts. Now this helps us set the values for the input also. So before we go there, let us fix, now that we have fixed the overdrives of all M3 to M10, let us now derive the W over L. We are going to derive the values of W over L. So W over L of 9 and 10, because we have fixed the currents and the overdrive voltages, you can calculate this. It turns out that W over L of 9 and 10 would be 400. W over L of 3 and 4 would be approximately 313, and W over L of 5 to 8 would be 278 approximately. So the once you have fixed this, we can now come up with the input levels also. Now since we have set unity gain, we will now say that VICM has two portions. One is the PGS of the input device and the VD-SAT of M0. And this has to be 1.35 volts, and now we are going to do somewhat arbitrarily say this is going to be 0.4 volts and this is going to be 0.95 volts. If we fix it this way, this will decide the VGS1 and the W over L of M1 and M2 also. So this will give you M1 and M2. Now you have all the sizes, width to length ratios of all transistors in the circuit, because you have now used the power dissipation condition and the overdrive swing limit conditions to arrive at this with some certain logical reasonable assumptions. So now the next step is to calculate the gain of this particular op-amp. So let us calculate the DC gain. To calculate the DC gain, we are now going to decide the GMs of the devices, and as you can see, W over L1 and 2, we will get a number of approximately 400 for this, and that will help us decide the GMs of the devices. So GM of 1 and 2 would be approximately 6 millisiemens. GM of 3 and 4 would be approximately 3.8 millisiemens, and GM of 5 and 6 would be approximately 50 millisiemens. And let us assume that, let us start off assuming you are trying to use minimum length, which is what you would do because you want to keep the parasitic capacitances as small as possible. So we are trying to find out if that would work for us. So if L is equal to 0.5 microns, this tells us that RDS of 1 and 2 would be the same as RDS of transistors 5 to 8. These would be approximately 13.3 kilo ohms. RDS of 3 and 4 would be twice RDS of 9 and 10, would be equal to 6.67 kilo ohms. Now note that first of all, the lambda of the PMOS transistor was already larger, so you expect the output resistance to be worse. You have designed them to have the same currents, and therefore the intrinsic gain of 3 and 4 of devices 3 and 4 are actually quite small. So please note that if you actually find out GM3 times RDS3, that ends up being quite small. So this is, you will soon find that this is going to affect us. So let us calculate the impedances looking up and down. So the impedance looking up is R up, and the impedance looking down is R down. The overall output resistance is R up parallel R down. So it turns out that for this particular circuit, R down is 8.8 mega ohms, R up is 66.5 kilo ohms. As you can see, because of the limited intrinsic gains of the PMOS transistors, your upwards impedance is much smaller than the downward looking impedance, and as you might expect, since this is skewed in one direction, the gain, DC gain of the op-amp ends up being only about 400, which is very far away from 2000. So you will now have to iterate for the gain. Now the iteration needs to go in a reasonable direction. So now we need to figure out what is causing this lower gain. As you can clearly see, the first thing that you need to do is fix this, right? If you increase R up, you will be able to get better DC gain, because that is limiting the value of DC gain. So the first thing that you would do is, so we now want to improve this DC gain. So the things we'll have to do, the first thing we want to do is increase the upwards looking impedance, so that the overall R out would also increase. And this can be done in several ways. You want to consider first, because RDS 9 and 10 is 3.33 kilo ohms, which is extremely small, you first want to increase R up. So increase L9 and L10 to increase the impedance looking upwards. That is the first thing you would do. Note that that would increase parasitic capacitances at various nodes in the circuit. So the bandwidth of the op-amp needs to be kept in mind while doing this. So the second thing you can do is increase GM1 and GM2, because as you can see, for a gain of 2000, GM12 of 6 millisiemens is actually quite low. So you want to increase GM1 and 2, which means increase W over L of 1 and 2, because you do not want to increase the power dissipation. Note that again, this would increase the parasitic capacitance at various nodes in the circuit. And number 3, you want to increase W and L of M3 and M4, because the intrinsic gain is very small. So this, of course, again would increase the various parasitic capacitors in the circuit. So now you can use a combination of these three procedures to increase the gain, to the required value of 2000.